One of the many things you'll need to learn in physics and astronomy is the term luminosity. And we define luminosity as the total amount of energy emitted by an object as electromagnetic radiation per unit time. And the SI units we use for this are joules per second, which is also the same units we use for power. So we can also say the units for luminosity are watts. So an incandescent light bulb might have a luminosity of 100 watts, but the luminosity of our sun is about 3.9 times 10 to the 26 watts. And just to give you an idea of how big this is, I've written out this number in long form. So this is the total amount of energy being released from its surface every single second. But the important thing we need to remember about luminosity is this power output is not the same as the apparent brightness of an object. Now, sometimes we refer to an object's apparent brightness as its radiant flux intensity, or just flux. But an object's apparent brightness will depend on its distance from the observer. So let me show you what I mean with an example. Let's say we could fly out to Neptune, and then we turned to face the sun. Now we're so far away from the sun that it takes light over 4 hours to reach our eye after it leaves the sun's surface. The apparent intensity we receive from the sun, however, would be equivalent to having a 100-watt light bulb at 2.3 meters away, so about 7.5 feet. These two light sources would appear as if they have the same brightness. So in other words, their radiant flux intensity would have the same value. Now, how did I work this out? So I used this formula. So the radiant flux intensity is equal to the luminosity of an object that we're interested in divided by 4 pi multiplied by the radius or the distance to that object squared. Now 4 pi multiplied by the distance squared, that is equal to the surface area of a sphere. So if you imagine at the center of this sphere is the object that we're interested in, the object that is emitting light, and we've traveled a distance of the radius of a sphere. And we're interested in how much light is reaching us at this surface of this hypothetical sphere. And that's why we divide the total luminosity of this object, the amount of energy it's releasing per second, divided by the surface of the sphere. And that gives us our flux intensity in terms of watts per meter squared. And what you need to do, if you're studying physics, is be able to remember this formula and to be able to use it. So let me show you how I worked out my previous problem. So we start off with this formula, this radiant flux intensity formula. So we want our flux for our light bulb to be exactly the same as the flux intensity of the sun when we're at the radius of Neptune's orbit. So we can say the flux intensity of the sun is equal to the flux intensity of the bulb. Now we can write this out, we can expand this out by saying that the luminosity of the sun divided by 4 pi multiplied by the distance of the sun squared is equal to the luminosity of the bulb divided by 4 pi multiplied by the distance of the bulb squared. Now we don't know the distance of the bulb yet, but we've got the distance of the sun, we've got the luminosity of the sun, we know the luminosity of the bulb, which is 100 watts, and we'll need to rearrange this equation. So we know, because we got 4 pi on both sides of the equation in the denominator, they both cancel out. So we end up with this equation here, and if I divide both sides of the equation by the luminosity of the bulb, and I multiply both sides of the equation by the distance to the sun squared, we can move the luminosity terms to the left-hand side of the equation and the distance terms to the right-hand side of the equation. So we want to get rid of this squared term on the right-hand side, so we can square root both sides of the equation, which I've done, and we can write out the luminosity for the sun, the luminosity for the bulb, and the distance to the sun here. And the distance from Neptune to the sun is 4.54 times 10 to the 12 meters. And finally, we can rearrange this equation to get the distance from your eye to a 100-watt light bulb for the flux intensity to be equivalent. And we get a value of 2.3 meters. So why is it helpful to know an object's luminosity and to be able to measure its flux intensity? Well, with these two values, we can measure the distances to various stellar objects in the universe. So some of the objects we see in the night sky have a definite and fixed luminosity. And we also have electronic detectors that we can use to measure the flux intensity of various objects. And when we have the values of the radiant flux intensity of an object, and we already know its luminosity, we can use our flux intensity equation to find its distance. And all we need to do is simply rearrange this equation, which I've done here on the screen, to isolate the distance. Okay, let's try two quick questions before we wrap up this video, and I'll talk more about how we measure distances to stellar objects in the next lesson. So, the luminosity of the sun is 3.9 times 10 to the 26 watts. The Earth orbits the sun at a mean distance of 1.5 times 10 to the 8 kilometers. Calculate the radiant flux intensity of the sun near to the Earth. So, do you remember the formula for the radiant flux intensity? So the flux intensity is equal to the luminosity of our object divided by 4 pi multiplied by the distance squared. So all we need to do is plug in our values from our question. So the luminosity of the sun is 3.9 times 10 to the 26 watts, divided by 4 pi, multiplied by 1.5 times 10 to the 11 meters squared. And we have to remember to convert the distance in kilometers here to meters, and we simply multiply it by 1,000. So we get a value of 1.379, 0.34 and so on watts per meter squared, but because our values here in our question are only accurate to two significant figures, our answer can only be accurate to two significant figures. So I've rounded this up to 1.4 times 10 to the 3 watts per meter squared. The radiant flux intensity at Earth due to the sun's radiation is 1.4 times 10 to the 3 watts per meter squared, to two significant figures. The mean orbital radii about the sun of Earth and of Mars are 1.5 times 10 to the 8 kilometers and 2.3 times 10 to the 8 kilometers respectively. Determine the radiant flux intensity of the sun at Mars. So if we remember our equation for the radiant flux intensity, this is equal to the luminosity divided by the equation for the surface area of a sphere, so 4 pi multiplied by the radius of this sphere squared. The only variable that isn't going to change for our question here is the luminosity value of the sun. Now, we're not given this in this question, but we don't actually need it to solve this problem here. We can rearrange our flux equation here to make the luminosity of the Sun the subject of the equation. So the surface area of a sphere with a radius of the Earth's orbit multiplied by the flux intensity at the distance of Earth's orbit is equal to the luminosity of the Sun. But also, we can say that the luminosity of the Sun is equal to the surface area of a sphere with a radius to Mars' orbit multiplied by the flux intensity at the distance from the Sun to Mars. So we've got 4 pi on both sides of the equation, and this cancels out. We've been given the values for the distance from Earth to the Sun and the distance from Mars to the Sun, and we also got the flux intensity at the distance of Earth to the Sun. All we need to do is rearrange this equation to make the flux intensity at Mars's orbit the subject of the equation. And we get flux intensity at Mars of 595.46 and so on watts per meter squared. But again, our values are only good to 2 significant figures. So we get an answer of 600 watts per square meter to 2 significant figures. And if we have a look at the ratio of the flux intensity at Mars and the flux intensity at Earth, so Mars will receive about 43% of the equivalent flux intensity that we receive on Earth.